Hey everyone, this is Brian and Andy from the organizing team. It's our pleasure to host the data challenge this year. So first, let me give you some background information and motivation about the challenge. It's clear that in today's manufacturing, vision-based inspection methods become a trending technology. The tricky part is that real defects can not only be really complex, but also often rare and difficult to collect in production, especially when a new product just starts rolling out. This makes the ability to detect new defects with minimal data becomes a challenging yet valuable task for the industry. As a consequence, this challenge aims to address the data imbalance problem based on reference learning with visual prompts under a one-shot setting. To keep things practical, we are testing the solutions not just on defects from training sets, but more importantly, on images with higher resolution, where the defects could be really small and easy to overlook, and negative pairs, where the query image may not have the targeted defect, just as the most frequent case in production line, and even harder on out-of-domain defects that never appear in the training set. All of these capabilities is crucial for a pipeline to learn and scale in real cases. In light of this idea, our training dataset covers 5 diverse product categories, with defects from processing errors to physical damages. And the test set of 2,000 pairs reflects real-world scenarios, including positive pairs that matches what you have seen in training, and new out-of-domain defects, as well as negative pairs without targeted defects. This composition enables a thorough evaluation of the solution's performance in identifying both familiar and novel defects. For the evaluation part, we developed the Production Efficiency Score, or you can call it PES, to reflect challenges in the industry. This metric balances 2 key aspects, the catch rate for positive pairs and the yield rate for negative pairs. Catch rate measures successful defect identification with IOU above 0.3, while yield rate assesses correct handling of non-targeted items. By combining these scores, PS emphasizes the dual importance of accurately detecting defects and avoiding overkills, mirroring the complexity of actual production environments. Next, let me hand over the stage to Andy. He will share more details on challenge participation and results.
This is Andy. Let me introduce the participation and results of the challenge. We have over 80 teams registered for the challenge, representing 16 countries and regions. This year, more than 30 universities and over 10 companies are participating in the challenge. Let me walk you through the schedule of our data challenge. This year, we introduced a special test set called the beta test, which we released 4 weeks before the final test phase. Our goal was to give participants the opportunity to try their methods on the beta test before tackling the final unseen test data. We received 283 submissions during the beta test phase, demonstrating how helpful it had been for participants to gain hands-on experience. Now, let's review the final submissions. During the final test phase, 35 teams made a total of 523 valid submissions. Impressively, half of the teams achieved results that outperform our baseline method. From the box plot, we can observe steady improvement in the participants' methods, with scores increasing day by day as they refine their approaches. Lastly, we are thrilled to announce the winning teams of the data challenge. Some use simple yet effective assemble and divide and conquer methods, while others leverage the power of vision foundation models. We are also excited to see some truly creative thinking this year. We are delighted to have the winning teams with us today to share their methods and insights. But before we move to their presentations, we would like to extend our sincere appreciation to everyone who contributed to making this data challenge a success. And of course, a big thank you to all the participating teams. Thank you.
Okay, so maybe we can start our first presentation.
Hello everyone, my name is Gaopen Chen and worked in Luster. Today I'd like to introduce our champion solution for the VISION'24 challenge, SEVE, segment then verify. In order to deal with the deal with this complex issue, our SEVE follows a two-stage cost-to-find paradigm. During the first segmentation stage, we apply a divide and conquer strategy. A multimodal large model agent is used to dispatch the input data, following a product-aware segmentation. During the second verification stage, we performed a fine-grained inspection of defects to return the matched defect regions, leading to more accurate segmentation results. For the MLM agent, we hope it will help us with the following task. The first one, identify the product type. It can help us to achieve the product-aware segmentation. And the second one, review of segmentation results includes relationship judgment of the detected defects and detection of undetected SIMPs. Finally, mini interval with 4 billion parameters is used as our agent model, and we designed two conversation templates to fine-tuning the image encoder and language encoder with LoRa. Then coming to the product-aware segmentation, we directly stack the pre-image, support image, and support mask as 7-channel inputs, and use the mask-to-farmer as our segmentation model. Specific for the cylinder product, patch call is adopted for unknown logistic anomaly with missing structures. For the second verification stage, ResNet 18 is used as a validation model for each known product, and the inputs are corrupted defect images. For unknown product, we conduct the fine-grained verification with the MLM agent model, and it can be easily achieved by the designed conversation template. Finally, our SEVE achieved the first place on the leaderboard and achieved a significant improvement over baseline, and surpasses all other methods with a catch rate of 91.5%. And our SEV is the only approach to achieve over 90% in both catch rate and yield rate. Here are some visualizations of our results. The first column is the results of the segmentation stage, and the second column is the final verified results, and the third column is the support image and the support mask. As we can see, our SEVE can achieve accurate segmentation and effectively verify for negative pairs. That's all. Thank you.
Yeah, thanks for the presentation. And then we are going to the second prize. They share their recording. So Shansong.
Hi everyone. My name is Zhe Wang. I'm honored to participate in the second workshop on vision-based industrial inception. We are a team from Suzhou TZTEK Technology Company. Besides myself, the team members include Qi Fan, Peng Yang, Zhiming Chen, Jun Zhang, and Xiaoming Li. Qi Fan is an assistant professor at Nanjing University, served as our team's mentor. The training set for this competition includes 12 defected categories across 5 different industrial scenes: cable, cylinder, PCB screw, and wood, with a total of around 2,000 images in the training set. The final test set contains 3 types of data: known, unknown, and unseen. Known represents detects that are labeled in the training set. Unknown represents detects that never appeared in the training set. Unseen represents detects on a new product category that never appeared in the training set. Through data analysis and some experiments, we identified that following 4 challenges in this competition: small size of objects, query and support categories are different, unknown and unseen samples, and class imbalance. The purpose of the second step is to address the issue where query and support categories are different. We contact the images and masks from the training set as input to a classification network and train the network based on the 12 defect categories. During inference, we apply the same process to both the support and query data, image and mask, extract features separately, and then calculate the cosine similarity. By using a specified threshold, we determine whether the query and support categories are the same. Below are some model details of our pipeline method. Figure A and Figure B represent the network structure of SegGPT and HDMNet. Figure C and D represent the network structure of UNet and SegNext. Figure E represents the process of data synthesis for metric learning, and Figure F represents the network structure for metric learning. Below are some details of the experimental parameter settings for our approach, such as the backbone network, decoder, training and inference scales, number of iterations, and the resource environment required for the experiments. In results, present some experiments we conducted during the competition and their corresponding results. Table 1 shows that using only supervised method achieves a maximum PES of 0.59. Table 2 indicates that using SegGPT and HDMNet can significantly improve the segmentation accuracy for unseen and unknown categories. Table 3 demonstrates that using a matrix learning model can significantly improve the inconsistency between query and query categories. Here are some visual results from our model. This includes all the sharing of our approach for this competition. Thank you all for your attention.
Thank you. Now let's invite the third presenter from dinner team.
Okay, so hi everyone. I'm glad to be here to share with you or technical method. We are a team from dinner automation. Different from the previous method, we just simply consider this industrial defect segmentation as an offshoot of few-shot semantic segmentations. The background is that the model will require three input images: the support image, the support mask, and the query image. And the model need to predict the defect mask. So we simply borrow from the few-shot semantic segmentations. It's a model called the feature proxy transformer, the FP transformer. You can refer to the paper for more detail. So our pipeline is like this. So we have a dual vision encoder. So the first encoder is freezed, and it is used to generate the proxies. So what is a proxy? A proxy is the after this vision encoder, we will generate the foreground prototype and the background prototypes, and add learnable tokens to generate our proxy. Proxy is like meta knowledge that tell the model what it need to do. It need to segment the support image into a foreground mask, which is a defect, and a background prototype. After that, the encoder B, which is an encoder on the bottom, is a learnable one and served as the main learning process. It will extract the patch features from both support and query image. And before entering the first transformer block, the proxy features we previously generated are copied and concatenated to support and query patches separately. And the proc features interact with both the support and query features by attention mechanism. After each transformer block, the two sets of proxy features are merged, copied, and then concatenated as before. So this will enable the interaction between the support and query features and proxies. And the segmentation results are obtained by comparing query features with the foreground and background support features from the last block of our second learnable encoder. Besides the model overview, we also share some technical details. So first about data processing, because the image is of high resolution, so we will perform image slicing to generate non-overlap images, patches of size 448 by 448 using this SAHI implementation. So through this process, we will get more data for our training set. It's kind of data augmentation. And also, we will use a technique called visual prompt. We propose to add a visual prompt on images to enhance the feature representation in VIT. So specifically, we will apply red masks on the foreground region of the support images. And we found that this will enhance the sensitivity of the foreground feature matching. And also to better preserve the information from the shallow layers of the VIT, we also add a learnable skip connection. And this is the visualization of our prediction results. The first column is support image. The the second row is the support mask, and the third row is a query image, and the final row is our model prediction. So that's all. Thanks for watching.
Okay, thanks for the presentation. And last but not least, let's welcome our winner of the Most Innovative Award. To mirror the screen. Please go ahead.
Yeah.
Hello, I'm Donna Kim. Our team utilized visual prompting to perform one-shot defect segmentation. And to maximize its effectiveness, we developed cycle consistency-based uncertainty estimation. Let's revisit problem definition. There are support image and support mask that represent the defect we want to segment. And we need to segment the defect in the query image. Notably, we must also handle unseen defect that the model has not been trained on. Visual prompting is a method that enables one open set recognition through a learning process. Unlike typical recognition tasks, this approach focuses on matching the ROI with the query ROI. The model depicted below serves as our base model, where the visual encoder and prompt encoder extract features for the prompt and query, respectively, while the decoder is trained to match these regions. However, as highlighted by recent studies, open recognition models tend to exhibit bias toward thin categories. For instance, when an unseen defect is provided as a prompt, model often find the defect in the query image that it has previously trained. Participants in this challenge have likely observed this pattern. Now, I will introduce our method to address this issue. Initially, we predict the corresponding defect in the query image based on support image and mask, which we refer to as a forward page. In the subsequent reverse page, we perform visual prompting in reverse. Thank you. The model's predict query mask is treated as a form of support mask, and we test the model with predicting the original support mask. By calculating the MIOU between the ground truth support mask and the model's predicted support mask, we can quantify the reliability of the model's prompting results. If false positive occurs for seen defects due to the bias in the forward page, the model will struggle to restore the original support mask in the reverse page. We also weighted the scores for each page to enhance the reliability of the estimated confidence score. In our experimental results, we achieved 5th place on the real world without any special ensembles or complex network designs, particularly demonstrating a significant improvement in yield rate. Let's take a closer look at the inferencing example. At the top, we have a support image, and at the bottom, the query image. The red, green, and blue represent the support mask, predicted query mask, and the restored support mask, respectively. As you can see, in the left example, we prompt the model to find a black defect, which is an unseen category. A model segmented a white defect, which is seen category in the query image. During the reverse page, it is only natural that the model found the white defect in the support image. The right example follows a similar pattern. Although we prompt on unseen defect, the model segmented a familiar defect in the core image and failed to restore that. Through the cycle consistency estimation, we quantified the extent of bias in the visual prompting process and replaced the prediction with null. Now let's examine the good catch scenario. The model successfully segmented the prompt defect in the core image, and reverse case was also successful. As many of you are aware, OpenAI recently released O1 demonstrating induced scaling loss. It was shown that not only training but also prolonged inference enhanced model performance. I believe this approach will also be effective for visual models, and if we design models with greater flexibility, the quality of visual inspection can be significantly improved. Thank you for your attention.